Hi, I am Usman Anwar. Today I will be presenting our work titled Inverse Constraint Reinforcement Learning. This is joint work with Shayar Malik, Adil Raza Agassi, and Ali Ahmed. AI safety is a growing concern. For agents to be safe, they need not only be able to carry out a desired task efficiently, but also be aware of what behaviors are bad and should never be committed by that agent. These bad behaviors can be expressed in form of constraints. However, manually enumerating through all the possible bad behaviors is generally not possible. The natural question in this context is to ask that whether we can in some way automate the learning of constraints. In this work, we study this problem in the context of reinforcement learning agents. And we show that we can learn constraints in high dimensional continuous settings. Further, the learned constraints are reasonably general, and if we have learned constraints for an agent A, these constraints can also be used to train other agents which may differ from agent A in morphology and dynamics. The main focus of our work is on constraint MDP MC. MC is simply a typical MDP augmented with some constraint set C. Constraint set C contains those state action pairs which are physically possible for agent to execute but still should not be executed by the agent for other reasons. For example, for a chatbot, it is possible to be racist, but it still should never be racist because of ethical concerns. An important point here is that normal MDPM and constraint MDPMC generally have the same reward function. However, they still differ in their opt-in policies because of the errors of constraint set. The target constraint set is represented as C star in our work. This target constraint set is known to the demonstrating agent but is unknown to the RL agent. Formally, our goal is to recover a constraint set C which can best explain some demonstrations D from a constraint-aware agent when the learned constraint set is combined with the given normal MDP M. Note that we do not require these demonstrations to be optimal. The only important thing for this demonstration is to be that they should never violate the constraints. As the general rule in inverted forward learning, we assume maximum talking model. Further, the important thing in our formula is the indicator function uh, written here as indicator MC of top. This indicator function is equivalent to the constraint set C. That is, if for every unique constraint set, the corresponding indicator function is unique. Based on the observation, we target on learning this constraint set. We target on learning this indicator function. This indicator function distributes over residual state action pairs. Intuitively, this means that our trajectory is constrained if it contains at least one constrained state action pair. An example of this can be that a sentence uttered by a chatbot will be constrained if it contains at least one racist term. Using the assumptions shown in the previous slide, we can draw the following objective. This objective can be seen as trying to match the gradient of the log cost of the expert and the RL agent. In order to improve our training and to ensure that no pathologies occur, we use a regularizar. Regularizar ensures that the degenerate solution of constraining everything is not possible. Further, in order to accelerate the training, we rely on using samples from a previously trained agent when the constraint set was different from the currently considered constraint set. In such a case, we use importance sampling to get for the bias introduced. However, importance sampling can introduce a lot of variance. In order to control for the variance, we ensure that we break our update to the indicator function approximation theta theta whenever the L divergence between our sampling policy, and the target policy becomes extremely large. But these are hyperparameters which can be tuned. We varied our method on different environments. A grid environment where we show that our method can prevent reward hacking, and on two high-dimensional continuous state and action environments, half Lita and Moon and Ant environment. On all three environments, our method successfully trains the agent to not violate any constraints and still achieve high reward. Further, we show that constraint set learned from an ant agent can be used to train point and ant broken agents. In this setting, our method is the only one which is able to give good results at all. The baselines completely falter here. Finally, we conduct some evaluation studies. Our evaluation studies show that all the components of the algorithm are critical to its success, and removing any single component such as important sampling or early stopping results in subpar performance. Finally, we note that this work has quite a few limitations. For example, we only consider deterministic environments. We only consider hard constraints, and our method requires on-policy samples. Removing these limitations can be important future work in this direction. Further, we believe that our work connects with the research team of robust mutation learning, and future work can also be done in this field. Thank you for your time.